Alright, so the title for this lesson is Visualizing Solids for the Washer Method. And I should mention now that the entire purpose of this video is all to be about visualizing solids. I'm not going to be making any computations here. This is just going to be about seeing these things. So I'm going to start with one quick review question. And so first, this region R that we have here, this is the region I'm going to be working with for this entire video. I'm going to be revolving under all kinds of different things, so you should definitely pause and sort of, write that down, because I'm going to have to scroll it off the screen here in just a minute. So make sure you've got a decent sense of what that region looks like. All right? So the first question I'll ask is I want us to visualize what that solid would look like if it was revolved around the line y equals 1. And as a part of that, I want you to think about what shape are the cross sections. I should mention perpendicular to the x-axis. What are the thickness of those cross sections, and then what's an expression for the radius of those cross sections? So again, if you've got this region and you're revolving it around the line y equals 1, so you're taking this shape and sort of flipping it over the line y equals 1. If you haven't figured that out, pause the video and take a look. You should find that it's going to look like this, right? If you sort of see it, in fact, on this diagram, you can even see the blue line represents the curve. So you sort of got that shape, and you've got this sort of teardrop-shaped thing, right? That's the solid that we're talking about. If I take cross-sections that are perpendicular to the x-axis here, you should see that those are going to be circles, right? So to answer the questions I had, the shape, these are circles or discs. The thickness of those cross-sections, because I'm taking cross-sections perpendicular to the x-axis, we've been saying the thickness of these things is dx. And then an expression for the radius of the cross-sections. This again is a review of the things you saw yesterday. If we come back up here and look at this picture, we had said that we want to draw a line from the axis of revolution up to the function and say, okay, the distance between those things should be whatever the top function is minus whatever the bottom function is. So in this case, if we actually had to do a computation here, we would say that the radius would be the top function f of x minus the bottom function, which was effectively 1. That's what the radius of those cross-sections would be. So that's kind of a review of visualizing these problems when the disk method problems. We're now moving into this thing called the washer method, and I'll soon get to why it's called that. So my next question, I want us to visualize what this solid would look like if instead I'm revolved around the x-axis. So you can kind of see over here, you've got this blue curve, but instead of revolving it around 1, I want to revolve it around the x-axis, right? So what's it going to look like? And if you want to take a shot at that, you can. Otherwise, I'll just show you. So here you go. If I were to revolve it around the x-axis, all of that like white space between the blue curve and the x-axis effectively gets rotated around as well. And I sort of end up with this shape that's got a hole in the middle of it, right? And the question that I'm going to keep asking here is, what shape are the cross-sections? And if I turn this thing this way and sort of take a cross-section of it, I'm going to get basically, in some sense, a donut shape. There's a mechanical term called a washer. If you've never heard of one of those, Google for washer, and I don't mean washing, which is a little metal ring, basically. That's going to be the cross-sectional shape that we're looking at for all of these things, right? So when I revolve this thing around the x-axis, I'm going to end up with this solid shape, and the cross-sections are washers. Okay. My next question, what if I revolved it around a y equals -1? So again, we can go back up and look at this thing. If I revolve this thing around this line down here at -1, you can't even see it. Doesn't it just mean there's even more white space between your region and the line? Really should just mean that the hole in the middle of this thing is going to be bigger. Right? So if we scroll down and look at it, sure enough, you can sort of see the hole in the middle of the thing is bigger, but the key is that if I look at it, it's still just this ring shape. It's still this washer cross-section, right? So that's kind of what we're getting at there, right? So revolving around the x-axis, revolving around y equals -1, the difference we mentioned was just that you have a larger hole in the middle of it because there's more white space. And you can even see it here. The blue line is the curve. This little red line, if you can see it on your screen, the little red line is the axis of revolution. The cross-sections are washers. I'm going to sort of finish out this video by going through a few more pictures of these things just so you can get a chance to visualize them. And I really would recommend that you pause the video and try and visualize these before I show them to you. So what if I revolve around the line y equals 2? So I'll scroll back up to this thing. If I were to revolve this around y equals 2, this line up here, what would it look like? Well, notice that the curved function is red and the straight line function is green. When I scroll down, that's going to explain why this is all green. It's because when I revolve this thing around, the green line sort of rotates further around. And if we look at the inside of this thing, it kind of comes into a point because this curve comes right up to 2. So that's what that one should look like. My next question was, let's see here. Oh, there we go. We did y equals 2. What about y equals 3? Like, what if I revolved around something a little bit higher up? So again, pause the video, look at your original shape, think about revolving that around 3, think about what that's going to do. So, if I revolve it around 3, there will be a hole in the middle of it this time. And I get this sort of like smooth cylindrical shape on the outside, but on the inside of the thing, it's sort of got curved edges as it goes around. And again, you can sort of see that little blue line in there. And that's the shape we're working with. Once again, if I take my cross sections perpendicular to the x-axis, I'm getting this ring shape. And when we do the integrals in the next videos, we're going to be looking at that ring shape and finding the area of that thing. Okay? I think I just have a couple more. This time I want to talk about revolving around the y-axis. Right? What happens if I take this region that I have here and revolve it around the y-axis instead? Right? So imagine taking that region, revolving around the y-axis. What are we going to be looking like? We get a volcano. You can put, baking soda and vinegar and red food dye in the middle of it, and it explodes for your 4th grade science project. So we get the volcano diagram for that one. What happens if we revolve around x equals -1? So if we move the axis further over, just like we saw in the previous ones, it just means the hole in the middle of it is going to be larger. There's more room for lava inside this project. If I revolve around x equals 3, that puts the axis of rotation on the other side of the figure. But it's still just going to generate, it doesn't look like a volcano, it looks more like maybe a dog food bowl. Maybe that's what this is. The key piece I'm constantly going to be getting at, take a look at the cross-section. If I take the cross-section perpendicular to the y-axis, I get this ring washer shape. And calculating things is all going to be about that. So I hope that getting to see these things visualized sort of helps you to see them and helps you to see that washer. The next videos are going to be all about computation. So I will see you in those ones.